I was asked to take a little step back and look at kind of the past 10 years, where we've kind of come, take a little snapshot of today, and then try to look a little bit out. And Peter did actually a nice job of part of that, so I'll steal from him in that. But I realized a couple things as I did that. One is I realized 10 years ago wasn't that long ago. I feel like I'm really, really getting old now, because my children 10 years ago was an eternity. For me, as I was starting to think about where we were 10 years ago, I started to think back where we were 20 years ago, and then realized, no, it's been this time. So it became a little bit more manageable from that perspective. And the way that we see computing evolve in that time frame has actually been pretty interesting within both the industry, and I'll try to give a snapshot of this from how we see it from an industry perspective, and then how we just see it from a supercomputing perspective overall, and attack that from that perspective. And the one thing that I would say is I think a lot of things that have evolved to where we are today have been relatively evolutionary things. And we've gotten a huge way with relatively evolutionary thinking. And I think as we start to think about things going forward, a lot of new possibilities open up to us, which weren't really available before, and it's going to require us to think a little differently. And this isn't just over the next 10 years, but I think even just over the next few years, as some of the changes come down the pipe that Peter talked a little bit about, and you can start to think about a new way to manage your data and manage your computing environments in a very high-performance computing way. So I like this kind of view of what got us here today maybe isn't quite what we need to get us to where we need to go tomorrow, and a new way of thinking about it is required. When we think about it from an industry perspective, and we look at over the last 10 years and try to put ourselves back and think about the progress that we've made over the last 10 years, one of the big things is these new survey techniques that are really starting to drive model size and complexity. The PGS Triton survey, which was a few years ago, is a huge example of just a whole nother level in capability that's really starting for us to really make us rethink about how to do modeling and simulation in this way. An adoption of approaches, RTM has been here for a very, very long time. FWI is now getting pretty leveraged quite broadly now, and still has a long way to go as that evolves over time. But starting to use these techniques now is starting to drive a new need in the computing system, more from a capability standpoint than just a throughput or capacity standpoint overall in computing. Over the last 10 years, we pretty much have stayed mostly in this one-shot per node computing model within the industry, and that's driven a lot of our thinking, and we're going to come back to that point here in a little bit, because I think that that's one thing that is definitely going to change over time with the way that computing systems are going to align over the next few years. And obviously, our systems have gotten bigger. And as we move forward, that's going to continue, we believe. From a supercomputing perspective, we pretty much lived off the clock rates growing, and living off that has been a huge part of what we've been able to do with computing, and we haven't had to focus as much on making the entire system scalable. And all components, because we've been able to get a lot of our performance gains just from that individual core getting a lot faster over time. But what we have done, I think, as an industry very successfully is really driven the cost of computing down very substantially. And I think that that's a huge success story overall within the industry over the last 10 years, to really focus on getting that cost of computing down quite a bit by leveraging a lot of commodity technologies and new computing technologies at the same time. As we take a snapshot today about where we are, I would say that these new survey techniques are still driving a lot from the industry standpoint. really starting to challenge to get new science out of the machines, much, much more clarity in our models and much, much finer grain resolutions in that, and workflows becoming so much more important than just the individual simulations or models that we're doing. It's all becoming much more about the workflow and putting a lot more pressure on how we manage the data through that workflow, something that Peter talked a little bit about here. I think another thing that we're starting to see from a number of industry leaders is starting to think about transitioning from just pure driving the cost out of computing to, is there a way to use computing to get a competitive edge in the industry? Still focused on return on investment, so not giving up that side of things, but is there a new way of thinking about this? Can I take advantage of, with this huge growth of data, can I take advantage of this in a unique way now and start to thinking about my computing environment differently, still being able, though, to justify how I'm doing that from an ROI perspective within the industry, which is a good balance point, I think, overall. We're starting to see data sets grow tremendously, even just over the last couple years, starting to get very, very big data sets overall. And we're starting to, as we talk with customers around the industry, people are starting to plan for some pretty large systems over time and starting to think about how do we manage, how do we use that effectively within our environment. And that's kind of a snapshot of where we are today from the industry. And then when I look at it just from a supercomputing perspective, single cores are getting slower. They haven't stopped, they've actually gotten slower. And so now how do we start dealing with this and starting to think about a socket and a computing, where's my computing environment overall? This really has changed things overall. And one of the big things from a system standpoint today is that it's really about throughput of that machine. We used to be very, very focused on individual feeds and speeds. We used to talk about our line speeds a lot and what are our SerDes rates and what type of lithography are we on and all of those kinds of things. What we're finding is those things are getting really less and less important overall, and it's really about congestion in the system and how do we manage this congestion overall within the machine. And this has become a really, really huge change for us over time. We've found, for instance, a commodity system at Cray. We sell both, of course, commodity systems as well as very tightly integrated high-end supercomputers. So we get to do a lot of looking at these two environments and comparing them head to head. And understanding kind of the pros and cons of these different environments, which is really, really important from an operational perspective. But what we found is if you look at commodity systems and you just run a single benchmark on the machine, an otherwise idle machine, especially if it's a little toy benchmark, overall, you get very different results than when you start loading this machine with lots and lots of different applications and you start to get a lot of cross-talk on the interconnect and things like that. These are where things start to matter. For instance, just an optimized MPI library, and when I say optimized, I'll say the standard is an MPitch library. What you would get from an Intel package would be kind of the normal standard that everybody gets to use. Optimized libraries, we're seeing 30 and 40% differences on a loaded system. Interconnects from a standard, InfiniBand network or something like that, you can get 50% better performance and capabilities. Line speeds and such, bandwidth and latency numbers look relatively similar, but it's all becoming about how do we control congestion on the machine? How do we do retries? How does job placement affect performance and capability of the system? And all of these kinds of things that are really, really starting to matter much, much more from a supercomputing perspective. And then, of course, parallelism being really the way that we're going to broadly get to here. And so a lot more work around tools to understand our applications and understand the hotspots and how to parallelize them, libraries to more efficiently lay out the machine and take advantage of it. It's really becoming about how much efficiency can we get out of each of those individual processors. There's a great discussion in the industry and the interconnect side about should you do offloading of the processing of the network onto the network, or should you process it on the node? I'll tell you that that's not a very important discussion, quite honestly, because we don't use all of the capability of a node anymore. There's a lot of free cycles on that node that we can take advantage of. What's more importantly is how we're managing all of this from an overall computing environment. And so that's kind of a snapshot of where we are today and over the last 10 years. So we've come quite a distance, I think, over that time. Now, the harder thing, of course, is to start to look out in time. And what do we think that things are going to do over the next few years? And one thing that we're hearing a lot from many of you is that you're believing that just over the next few years, the processing capabilities are going to go up about an order of magnitude, and over a 10-year period, a couple orders of magnitude from where we are today, which is starting to be really, really challenging. And there's a lot of crossovers between a lot of other industries that are traditionally using some of the largest supercomputers and what we've used within the oil and gas field, which are very large themselves. ResSim becoming bigger and bigger and more important, really not being relegated to a very small part of our computational mission, but potentially can start to do really, really interesting things on the ResSim side, not just the seismic side of the house. And that's I think, very exciting for us overall. We've had some recent examples I'll talk about in a second of some really amazing ResSim results overall. And we're starting to see from all of you a discussion around how do we take advantage of what's going on in this big data analytics world, what's going on in deep learning and artificial intelligence, and is there a way to kind of more optimize the workflows and the quality of results that we're getting by bringing these technologies together overall over time. When we look at kind of what's going on in the industry over the next 10 years, I've mentioned parallelism. I'm just going to say it's parallelism everywhere, through all layers of the system, whether that be threads becoming much more important than cores or nodes as we start to think about these systems overall, and start to be how do we manage these potentially millions of threads that we have on these systems that are all going in parallel. Application architectures are really starting to change as systems become wider and wider, not getting individually faster as we talked about, just getting a lot big, kind of like me, getting wider as we go out in time overall. I mentioned about the interconnects as we start to think about managing congestion and throughput on these networks is becoming more and more challenging. How do we start to deal with things in order to be cost effective of these resources, we have to keep them very highly utilized. Much, much more highly utilized than typically is done in commercial IT, for instance, where maybe people are happy if they can get to 30 or 40% utilization on their machines. We're in the 90+% utilization of machines, and that's causing more and more congestion. And as the nodes, as we'll talk about, get higher and higher performance, it puts much more pressure on the interconnect and the network within the system than we have had in the past. And so we have to start thinking about those things as a much, much more important thing, because the bandwidth ratios of the machines are not what we typically have seen over the past few years. They're getting really different. And even though we're not moving like from the good old days of Cray, of vector technology, to MPPs or clusters, we're not seeing that kind of a shift overall. Architecturally, it's causing almost the same amount of change within the machines as we go forward in time. Peter talked a lot about the memory and storage hierarchy, and I'm going to come back to that a little bit more too. But I would say that the biggest change that we're seeing in the systems is the memory and storage hierarchy. That is where a lot of the magic's going to be is how do we take advantage of this really deepening hierarchy of both memory and storage. And I thought Peter did a really great job at talking a little bit about this. Processor choice is going to start to grow again. So as we look around the industry at the systems that we have out in most of the major oil companies and processing companies, it's mostly Xeon or GPUs. That's what we pretty much see today. We will continue to see those, but we'll start to see these many core processors, Xeon Phi. We'll see more options, with AMD and ARM and other processors like that starting to come in. FPGAs playing an interesting role as they get more integrated on the silicon with the processors, technologies. So we're starting to see a lot more options there. And we think that over time, systems will become more and more heterogeneous because these different processing technologies all have different pros and cons, and not all fit every job. But what we really want to do is start to manage all of the data of the machine as tightly as we can. So instead of having separate machines to do all of these things, we believe that we're going to converge all of that into one central system to manage so we don't have to move data because it gets very expensive to start to move it from a very high performance network on one machine off to a lower performance network and back onto another high performance network on another machine. And so we'll see some convergence there overall. And while I was only asked to look out the next 10 years, which I think CMOS feels really good to me over the next 10 years. As we start to think about beyond 10 years, we're going to have to start to think a lot more about, as we already are today, what's next? And that's a really tricky question overall, I think, as we go forward in the industry. So I think that this next round, exascale systems, this next 1,000 that we're going to get over the next few years, is going to be the last 1,000x of processing that we're going to get in CMOS. And if you want to go further to Yada scale or Yada flops, I don't think that that's probably going to be CMOS technology that's going to get us out in that time frame as we go forward. But I do want to talk just a little bit, and I'll try to talk a little bit from where Peter just took you a little bit ago and look at it from a whole system perspective. When we see that these are systems in the next few years, by the way, this is not looking out 10 years yet. This is less than a handful of years that we'll start seeing 10 plus teraflops on a single node with very, very wide vectors, or GPU-style computing on that node. And so we need to think about how we're going to organize our applications to take advantage of those much wider vectors that we're going to have overall on a node. So a node is going to become very, very high performance. Again, shifting completely the balance of the system out to these nodes. We're already seeing some vendors starting to think about architectures where a node is even heavier than this. So where you could have another order of magnitude or two out in each individual node, which I think is not very balanced when we think about a big scaling system. But for smaller scale jobs, I think that those are kind of interesting to have big fat nodes out there if you can run your whole job in a node. Once you have to start to scale nodes, you need to think about overall system balance. It's kind of like GPU computing today. If you can keep your model in a single node, you can put 4 or 8 GPUs on a node, and that's kind of makes a lot of sense. If your model has to scale beyond that, you don't want that much GPU computing out on the node. You want to more balance it with your interconnect bandwidth, because now you're worried not about the bandwidth between all the GPUs on a node, you're worried about the bandwidth between all the GPUs on the system. And so you need to change that ratio. And so we're seeing more of a 1-to-1 or 1-to-2 ratio for jobs that are scaling beyond a node. And we have to start thinking about this in the same way as we go forward. I completely agree with Peter on the on-package memory, the high bandwidth memory. That is going to be critical overall. But it is also going to probably cause one of the biggest changes in this industry, which means the amount of memory that you have in that high bandwidth package per how much flops you have in that node is a ratio that is way different than we have today. And so this kind of one shot per node model will be highly, highly inefficient in these systems over time. And that is a huge change overall, I think, about how we have to think about computing going forward, because you're not going to want to leave that high bandwidth memory if you don't have to, because the next level, as Peter talked about, as you get out to like non-volatile memory, 3D cross-point, or things like this, they start to not feel like memory. Even though you can access it like memory, it starts to feel so far away that it starts to look more like local disk on your machine that you can read and write to just like memory. And flash starts to become the next storage. So that kind of the tiers of the storage hierarchy all start to move up and really, really deepen. Overall, disk starts to look like archive or campaign storage, as Peter talked a little bit about, and how we manage that. So this is a really, really big shift overall in this kind of memory and storage hierarchy. That's a big change overall. From a system perspective, we're going to get very, very high performance interconnects. They're going to be very fast, and also thinking about huge systems with 1 or 2 or maybe 3 hops to get across the entire machine. So very, very low latency, very, very short hop networks overall. But systems kind of on order of 100,000 nodes, 10 to 100 million system threads on the nodes. And again, I think that when we think about the parallelism, the threads are what we should really think about. That's how we see some of the largest systems in the exascale era starting to play out. But those same system structures is what's going to be handled at even a single cabinet of a cluster today, because you'll have those same technologies that you can use in that environment. And so that's, I think, a huge change of how we're thinking about computing over the next few years. It's going to cause us to rethink a lot of the modeling that we're doing today. And there's been some great work on that overall. The other thing from a Cray perspective is, since our founding with Seymour, we've really only focused mostly on scientific and engineering models. That's really what we've done, is taken a scientific and engineering model, let's call it a seismic model, put that on a supercomputer, and try to show the best, prettiest picture that we can of what the subsurface looks like. And more now, people are trying to say, can we integrate this with analytics? Can we start to integrate this with tools like Hadoop and Spark and different kind of analytics models? Can we start to do the same thing with deep learning and artificial intelligence models and start to bring these together? Because today we think about these as completely different systems. We're going to do our deep learning over here on this machine, and then we're going to do our modeling on this machine. But overall, what we really want is we want the outputs of these to affect the inputs of the other. And the outputs, it's almost like pre and post processing in a constant loop as we think about the workflow. So more and more we're going to want these integrated, again, on the same system, because we don't want to be able to have to move data off that machine going forward. And then, of course, we have this huge flux of data coming into the systems that we're going to have to deal with and build these models from. And some of that is streaming data over time, not just single data sets. And so what we've really been starting to think about is, in this model, this converged model, how are we going to compute in this environment? How are we going to store and manage our data in this environment? And how are we going to do analytics in this environment together, so we can come up with a better answer and a better solution overall? There's some great early work done in here. I'm going to share some work by PGS that's pretty amazing. They did this really impressive survey called Triton. And I know that you guys, most of you in the room, have heard about this story, so I cannot do it justice. But at a computing perspective, really looking at a very, very large data set, over half a petabyte of data, and doing that in memory across the machine on a globally addressable memory. So how do we lay this data out across an entire machine, not kind of the traditional, again, one shot per node model, and use FWI as part of that. And we've been very excited to be able to work with them to do this kind of a model. And one of the first questions is with this size of data, is there a better way to compute this? Is there a different way to compute this than we have been doing on our commodity cluster technologies overall? And we work together to figure out how to take advantage of some unique supercomputing technology in order to do the computing part in a different way. But what's even more exciting is some work that they did recently with some partners at Rice University to start to think about, can we start to do this convergence between big data analytics and machine learning and artificial intelligence with what we're doing on the modeling side. And they looked at the BP velocity model benchmark. And you can see that here on the left. And they basically, the way that they do this today is they manually pick and optimize around a velocity model. And you can kind of see the result with FWI here in the middle about what they're able to simulate, which is quite a bit better than they've ever been able to do before. And then what we've been able to do, and this is a little video here, with machine learning is iterate on choosing the best velocity model that they could find over time. And we can get over time through these iterations to a much better answer. And so this is, I think, just a great example and just a sneak peek at what I think is possible in the future as we start to integrate the capabilities of deep learning and artificial intelligence with our traditional world of modeling and simulation. And there's some other great examples of people really starting to push out today already and starting to think about how do we use this technology in new and unique ways. Our partners from ExxonMobil ran a 700,000 processor plus ResSim job on the Blue Water system at NCSA. Really an amazing result, thousands of times better than they've been able to do before on that model. So a really exciting, I think, example of using these technologies. At KAUST, I know David talked earlier, I'm sure he talked about what they've done with Saudi Aramco in doing a trillion cell reservoir model on their full machine at KAUST, almost a petabyte of data that they used on this model. These are like amazing numbers overall that people are doing today on these systems. Which is super exciting. And PGS, as we just mentioned, 200 gigabyte data set per shot on their machine with a 600 terabyte data set. So really, really interesting, I think, of companies today that are really starting to think about taking advantage of these new technologies and what they can provide. And I will tell you that, as I've shown, the world is shifting over the next few years, and I think more and more of us across the industry will have to start thinking about how do we use this technology different over time. So I'll stop there. I really appreciate, again, being able to come out here. And I do think that while what it took us to get here is probably a little bit different than what we're going to do over the next few years, I do think that there is a pathway to get there, and one that, as an industry, I feel really confident that we'll be able to solve together. So thank you very much.
Thank you.